Now I'm going to prove the variance of gamma distribution. I want to prove that the variance of gamma distribution is equals to alpha beta square. How am I going to establish this fact? I am going to use the density function just the way I use it when I was proving the mean of gamma distribution. So therefore, the variance E of x squared is equals to the integral 0 to infinity x squared, okay, x squared times f of x dx. So substituting this in the formula, I will now have the integral 0 to infinity, okay, x squared, then the function f of x dx represents the density function f of x of beta, which is 1 over beta power alpha gamma of alpha x to the power of alpha minus 1 e to the power of negative x all over beta dx. Okay, beta dx. So 0 to infinity x2 plus alpha minus 1, okay, e x all over beta 1 all over beta raised to the power of alpha gamma of alpha dx. So writing the constant out as usual, I will now have 1 all over beta power alpha gamma of alpha, the integral 0 to infinity of x, okay, so 2 minus 1 is 1, so I will now have alpha plus 1 e to the power of x all over beta dx. Is it? So I will now introduce my new variable t. I will make a supposition, let t be equals to the power x all over beta, so that x, okay, is equals to t beta, so that my dx is now equals to beta dt. Okay, so by substituting this newly introduced variable, this will now change to 1 all over beta power alpha gamma of alpha, the integral 0 to infinity. So my x to the power of alpha plus 1 will now change to, because x is equals to t times beta, therefore I now have t times beta raised to the power of alpha plus 1 e to the power of negative t, okay, and the x is equals to b dt, so beta dt. Is it? So I will now have 1 all over beta power alpha gamma of alpha, the integral 0 to infinity t power alpha plus 1 beta, okay, power alpha plus 1 okay, times beta times e to the power of t, then dt. So by bringing out the constant, I will now have uh, beta to the power of alpha plus 1, beta alpha plus 1, then I now have beta again times beta, so that's all I have, all over beta to the power of alpha gamma of alpha integral 0 to infinity t to the power of alpha plus 1, okay, e power negative t dt. So here the constant can be written as, beta to the power of alpha plus 1 can be written as beta power alpha dot beta, okay, dot beta all over beta to the power of alpha gamma of alpha, so that this will cancel this, okay, 0 to infinity integral t to the power of alpha plus 1 e to the power of negative t dt, okay. So we now have beta square all over gamma of alpha, the integral 0 to infinity t to the power of alpha plus 1 e to the power of negative t dt. Also, it is a well-established fact that uh, the integral 0 to infinity t power alpha plus 1 e negative t power 1 dt is equals to gamma of alpha plus 2. Gamma of alpha plus 2, because here is alpha plus 1, just like the way I have already explained it. And gamma of alpha plus 2 can be written as alpha minus 1 no plus 2 alpha minus 2 plus 2, then gamma of alpha minus 2 plus 2, okay. Here gives us alpha plus 1, and here gives us alpha, and here gives us gamma of alpha. Therefore the result, beta square over gamma of alpha integral 0 to infinity of t power alpha plus 1 e to the power of negative t dt can now be written as beta square over gamma of alpha dot alpha plus 1 alpha then gamma of alpha. So when you look at this line, gamma of alpha will cancel gamma of alpha, leaving us with beta square alpha plus 1 alpha, and then this line can be written as beta square alpha square plus beta square alpha, okay. But we are not done yet. We need to establish the fact that the variance is equals to alpha times beta square. Now the variance is equals to e of x squared minus e of x all squared. So recall that the e of x squared is equals to beta square alpha square plus beta square alpha, which is the result we just found. And e of x, that was the first result we got. That is the mean for the gamma distribution, which is alpha times beta. So substituting here in order to find the variance, I'll end up getting the variance to be equals to e of x square, which is beta square alpha square plus beta square alpha minus then the first result, which is alpha times beta all square, that is alpha times beta all square. Okay, so simplifying this further, I'll now have beta square alpha square plus beta square alpha minus alpha square beta square. So what is alpha square beta square? This is alpha square beta square regardless, because it can be written in the switch. So this take care of this, leaving us with beta square alpha. Therefore the variance has been proved to be beta square alpha square.